All right, we are here to talk about Chapter 3.4, the infinite geometric series now. So now we're going to infinity. It's on page 90, I believe 97. Needs to be updated. But let's look at the general formula to find the sum of an infinite geometric series. S sub infinity, going out to infinity. We keep going and going and going and going. A sub 1 divided by 1 minus r. A sub 1 again is the first term. R is our common ratio. Again, common ratio can be found by taking a sub 2 and dividing it by a sub 1. All right, so we have some things to consider with r, because R really determines whether we are going to have a sum or not. So two things we want to consider is, does that R value converge to a certain value, or does it diverge to another value? Well, in essence, if we diverge, that means we're getting farther and farther apart, right? So if a number grows exponentially, then we're getting farther away, and so we can't ever find a sum. Because if it goes 2, 4, 6, 8, then we're getting bigger numbers and bigger numbers and bigger. So if we kept going to infinity, all the way we kept getting bigger and bigger and bigger and expanding the universe with these giant values. Well, we don't want to do that. We can't find a sum that way. However, if, on the other hand, our R value converges, so we get a form where we have the values of the series starting to converge to a specific number, typically 0 or other numbers, then we will find that our R value needs to be some type of fraction. And that's what this means. The absolute value of R is less than 1, but it's also greater than 0. Because we could have something that's being multiplied by -2 and -2 and -2 and -2, and that number could still be growing. Although it's getting bigger negatively, we could still have growth there. So we want that R value to be something that's going to continue to break a number down, and that's what the fractions do for us. All right, so let's look at how we can find the sum. So example number 1, find the sum of an infinite geometric series. It goes 2 plus 3 plus 9 halves plus 27 fourths. First thing we want to do is look at R. Our R value is 3 divided by 2. And we ask ourselves, is that a fraction? Yes, it is. However, is it less than 1? Okay, we talked about earlier that's a fraction, but don't be fooled by some of those fractions. If it is greater than 1, which it is, 3 halves is 1 1/2, then there is a sum? No sum. No sum for you. Okay, then we can look at example number 2. And example number 2 says, find the sum of the infinite geometric series. This time we get 18 minus 6 plus 2 minus 2/3. And these are the numbers we come up with for our series. Our R value, a sub 2 divided by a sub 1, we get an R value of -1/3. So we can plug this into the formula because now our R meets the constraints. Okay? So once those R meets the constraints, then we can start to work with the formula and see if we can find a sum. We get 18, which is a sub 1, divided by 1 minus a -1/3. In this case, we can distribute that negative, and we get 1 plus 1/3. So 18 divided by 1 plus 1/3. Well, that means we get 18 divided by 4/3, because we could change 1 into 3/3, and that becomes 4/3. And we get 18, then if we have something being divided by a fraction, if you recall, we flip it and multiply by the reciprocal. So we get 18 times 3/4, and now we can take 18 and 4, we can simplify to 9, and that becomes a 2. So 9 times 3 is 27, and we get 27 halves, which 27 halves is about 13 1/2. So, and again, at this point, I remember when I was in this class years ago in my math class, and my teacher told us that there was this value, like I'm telling you, 13.5. That's all you're going to get. So we keep going on and on and on forever, right? We keep adding up numbers. We could go around this room and around the universe and everything. We would do all that, and all we'd end up with is 13.5. That seems pretty wild. Anyway, I'll let you ponder that. Enjoy, and thank you very much for watching the infinite geometric series. Have a good night.